Chapter 10, exercises 15 and 16, are asking about buffers. Now, the purpose of a buffer is to maintain the pH of a solution. The whole point of having a buffer is to prevent the pH of the solution from changing. Remember that pH tells you how a solution uses charge to push and pull on the stuff in it, to squeeze the stuff in it. If it's an acidic solution, it has a lot of H+. In other words, it has a lot of plus charge. And a solution that has a lot of plus charge will push on things that also have plus charge and pull on things that have negative charge. So that'll squeeze things in one way. Remember that a basic solution has a lot of OH-, and so it has a lot of negative charge. So it will push on things that have a negative charge and pull on things that have a positive charge. It'll push and pull, it'll squeeze stuff in a different way. So the acidity, the pH of a solution, tells you how that solution pushes and pulls or squeezes on anything inside of it, using the charge in the solution. Now that's really important for living things, because the message and the behavior of molecules in living things depends on the shape that they have, sort of like the way that the ability for a key to turn an engine on or to get you inside of your house depends on the shape that it has. So if those things were suddenly squeezed into different shapes because of the pH of a solution, they would no longer work, and the living thing that depends on them dies. So living things have a lot of buffers, and the purpose of the buffers is to keep the pH inside those living things the same. So how do buffers work? We talked about reversible solutions, and a buffer is a reversible solution. So notice that arrow there has an arrow going forward and an arrow going back. It's a reversible solution. On one side of the arrow, there is an acid. You can recognize it by the H in front. On the other side of the arrow is a base. Now this is a Bronsted-Lowry base. You can recognize it by the negative charge. Remember, Bronsted-Lowry bases are anything that can accept a proton, can accept an H+, and that's anything that has a negative charge or a lone pair. So what happens here? When you add an acid, the base gobbles it up, and equilibrium shifts to the left to reduce the amount of base. When you add a base, the acid gobbles it up, and then equilibrium shifts to the other side to reduce the amount of acid. So anything you add to the solution will be neutralized. If you add an acid, it will be neutralized by a base, by the base that's there. If you add a base, it'll be neutralized by the acid that's there. And that is able to neutralize any sort of acid or base you add to the solution. Okay, so given that sort of framework, let's see if we can work our way through the different questions in these problems. Now these are sort of multiple choice questions. A says the purpose of a buffer system is to, and we just saw that the purpose of every buffer system is always to maintain pH. It's to prevent changes in pH. Now, B says the salt of a weak acid is needed too. And so at first blush, it might not seem like there is a salt here at all. But look at the instructions. They say, consider the buffer system of hydrofluoric acid, HF, and its salt, NaF. So NaF here is the salt. And you know it's a salt because you have a metal and a nonmetal. And that's anything that has a metal and a nonmetal, any ionic compound, is also called a salt in chemistry. So what does that NaF do? Why would you add that to a solution? Well, you have the Na, and then you have the F. They're a solution outside of water, but when you put them into water, they each go their own way. The Na has its plus charge, and the F has its minus charge. And so you can see how after you put them into water and they go their own way, NaF really produces F-. And so when you want to create a buffer, you need the acid and the base. That salt is a way of adding that base to make sure that it's there for the buffer. So the salt of the weak acid, here's the weak acid, here's the salt that's relevant for it. That salt is important because it provides the conjugate base. It provides this F- that will be there to neutralize any acid that you add to the solution. Okay, how about C? C says, if OH- is added, and keep in mind, OH-, famous base. So if a base is added, it is neutralized by what? Is it neutralized by the salt? No. Remember, neutralization is where an acid combines with a base. So we're looking for some sort of an acid to combine with this OH-. And a salt is not an acid. A salt is an ionic compound, and even if after it breaks apart, you only get the F-, which is technically a base, so it's not the salt. Is it neutralized by H2O? H2O can act as an acid, but in this reaction here, it starts with 2 H's, ends up with 3, it's accepting an H+, so it's a base. You can go back to those problems here, the very first 2 problems in this chapter to see the reasoning for that in more detail. But H2O is actually acting as a base here. So instead, the only thing here that could be acting as an acid is H3O+. In the reverse reaction, that starts with 3 H's, it ends up with 2, and so it's giving away its acid, it's giving away its H, so it acts as an acid. And the H3O+ would be the only thing that's listed here that's an acid. That's what could gobble up the OH- and neutralize it, if that were added from those choices. How about D? If H3O+ is added, the equilibrium shifts in the direction of what? And this is this is going back to Le Chatelier's principle. The first thing you'd want to do is to figure out whether H3O+ is a product or a reactant. Remember that reactions are divided into 2 sides, the reactants on the left of the arrow and the products on the right. And you can compare that to these 2 sides of this water tank. So H3O+ is a product. We can see it here. So when you add it, that would be like adding water to the product side of this water tank. The water doesn't just build up there in a block. It flows. What direction does it flow in? It flows to the other side, to the left. So, toward the reactants, in other words. So when it says, if H3O is added, the equilibrium shifts in the direction of the reactants. Because when you add water here, the equilibrium shifts to reduce the change. Okay, so that's 16, or that's 15. 16 is a very similar problem, only they give you a different buffer solution. You have your acid, and you have the conjugate base. And those 2 will help to neutralize any acid or base that you put in the solution and keep the solution at a relatively constant pH. So one thing you definitely want to remember, the purpose of this buffer system is to maintain pH. A buffer system keeps the pH of a solution the same so that it squeezes the stuff inside it in the same way so that anything inside it retains its shape and so continues to function in a living system. B, it says the weak acid is needed for what? So the weak acid would be, you have a couple weak acids here. You have HNO3 and you have H3O+. The weak acid that they are probably referring to is the nitrous acid, because that's what's given in the prompt before the equation. So they say the weak acid is needed too. One thing an acid can do is neutralize base. Now it doesn't provide the conjugate base. As we saw in the last one, the conjugate base is provided by the salt. If you add the Na and the NO2, NO2 is a polyatomic ion, into solution, once they hit water, they go their own way. They each then have a charge, and that produces this NO2- that you see in the problem. So it's the salt that really produces that conjugate base, the NO2 minus. So it's not this first one. Now, any acid can neutralize a base. What we have here is a base, and so the acid can definitely neutralize that. To provide the conjugate acid, that just doesn't make sense. An acid wouldn't provide a conjugate acid. If it became a conjugate acid, it would start acting like a base, because it would have to gain one H+. So that third one doesn't make sense either. So there would be 2 for that. How about C? It says if H3O+ is added, what is it neutralized by? H3O+ we know is an acid, because it has lots of H's to give away. Is it neutralized by a salt? Well, you could argue that it is. It's not neutralized by the salt itself, but it's neutralized by something that comes from the salt. So if you wrote down 1, I would accept that. Is it neutralized by water? I would accept that too. After all, water is acting as a base. It starts with 2 hydrogens, it ends with 3, that means it accepts H+, so it could accept H+ from the H3O+. So I would accept 2 also for this. 3, it says OH-. There is no OH- here, and so there's no way for OH- to be able to neutralize anything, even though if it were there, it would neutralize H3O+. But it's not present, so it can't neutralize anything here. So either 1 or 2 would be acceptable for me. D, it says when OH- is added, so here we're adding what? A base. What direction does the equilibrium shift in? Now there's no OH- in this whole equation, but what would the OH- react with? The OH- would react with the acid, and it would take it out of solution. When the OH- reacts with the H3O+, it destroys it. It turns it into 2 separate water molecules. One of the H's goes over here, and that gives you 1 water molecule, and then what's left is the other water molecule. In other words, the OH- takes this H3O+ out of the solution. H3O+ is a product, so this would be like removing products. When you remove a product, we saw with Le Chatelier's principle, equilibrium shifts to the right. The water would flow to the right if you punctured a hole at the bottom of the tank here. And so equilibrium would shift in the direction of the products. When OH- is added, the equilibrium would shift in the direction of the products. So this is a general sense of how buffer systems maintain pH using Le Chatelier's principle.